Welcome to Learning AI. Today we're going to be learning how to implement a 2D linear regression model to analyze some house price data that I've downloaded from Kaggle. So we're going to be using Python with Jupyter Notebooks. If you want to get the same data set, you can just sign up to Kaggle and download the same data set yourself. I'll put a link in the YouTube description below as to how to do that. So let's get started. The first thing we're going to do is we're going to analyze the data that we've got. So to do that, we're going to need some libraries. So we'll import some libraries. That's not how you spell libraries. Here we go. Import numpy as np. We're going to use numpy because there's a little bit of linear algebra involved in the machine learning, which we'll do later. We're also going to import pandas. That's pd, and that's to work with the CSV file that we've got. And we're also going to import matplotlib.pyplot as plot. Matplotlib is so we can visualize our data as we go, which is very important in machine learning, because if you can't visualize your data and see what's going on, then it's very hard to make improvements on your algorithm. So, library's done. First thing we want to do is read our data and just have a look at it as a table. So, we want to read our CSV data into a data frame. Data frame is just the sort of like what pandas uses to hold your data in Python. So we use the pandas read CSV method, and my data is called kc house data.csv. Again, you can get that from Kaggle if you sign in. If you register, you can get that data from there and download it for free. So refer to the link in the description. So let's have a look at this data. I want to preview the top 5 rows. How are we going to do that? Pretty simple. Data frame dot head. It just shows you the top of the data set. So that's not quite right. That's why. Excellent. Okay, you probably found that before I did. So here's our data. Now there's actually like 20,000+ rows of data. I'm not going to list all that out. That'd be kind of silly. That's why I've just used the head function. So what have we got here? We've got ID, date. They're not particularly useful. That's just when the data was put into the data set. This is where it gets interesting. A house price. And then all these other columns describing that house that sold for this much money. So we've got bedrooms, bathrooms, how much living area, what total land area is, floors, it goes on, even the year the house was built. So all of these variables, all these features is the terminology we use in machine learning. So all these columns, all these features can be used to predict a house price. So we've got lots of examples here where we actually know the house price from having all these features, and we're going to try and use all this data to create sort of like an equation or a function that you can feed all these values in, where you know these values of the house but you don't know the price and you want to predict the price. So that's our goal today, is to make a house price predictor using all this information here for any random house. So let's get to it. Now, today we're going to be doing 2D linear regression because it's the first stepping stone to using the more complex things like multilinear regression. So 2D linear regression means we're restricted, unfortunately, to only having price and one other column, one other feature. So we're going to go with square foot living, and you'll see why in a sec. So what I'm going to do is plot this data so we can actually see what those two features look like. So we're going to plot it like X and Y data, so you just have a nice graph. So to do this, we're going to make a 2D data graph, and we want to just reshape our data frame just to those two columns that we're interested in, which is price and square foot living. So let's do that now. And all we're going to do is just list the names of the columns that we want. So this is why pandas is useful. There's this cool sort of way you can index things by their column names and things like that. So that's why we use pandas. Okay, so what we want is the price and square foot living area. Okay, and I'm going to set them as the X data and the Y data, just so it's nice and easy when we're graphing it. So data frame 2D, and the X data we'll call that square foot living. So you can see all we're doing here is in the data frame here, we're just getting all the values that are in the column called square foot living, and we'll do the same for the Y values. Okay, now we want to visualize the data, and when we do that, we will plot a scatter plot of X and Y, and we'll do the color of M and the marker of, so color magenta, so it'll be pink data, and then the marker will just do little dots. So it's pretty simple. We'll give it some labels. So our X label, we want that to be the column name. You know what? I haven't put price in here. There we go. We want that to be our column names, and there's a special method to do that as well with our data frame. So data frame 2D dot columns, that's going to get the column names, which in our case is price and square foot living, and then so that's going to be the 0th element, and that's going to be the first element of this column list. So the X label we want to be square foot living, the first element, and then the 0th element is going to be price, which we want to be the Y label. Okay, almost there. Plot show. Let's check this out. You put an equals in there. Excellent. So there's the data. It's a nice spread of data. You can see generally as the living area increases, the house price tends to increase as well. And that makes sense, right? If you got a huge house, it's probably going to cost more money to buy that house. So that looks good, that data. So, and it's sort of linear. I mean, if I was to draw a line through here, like that'd sort of fit the data, but I mean, if you wanted to perfectly fit the data with a line, it would be squiggling all over the place, and it'd be a polynomial of the millionth degree or something like that. So, but what we want to do is we want to generalize. We want to plot one line that fits the data as best as possible. So, what we're going to do is first we're just going to have a guess. We're going to manually just plot a line on, and then see what it looks like. And then we're going to think of a way of quantifying, in numbers, how well that line fits the data. Otherwise, we could just, it's a bit hit and miss, just visually putting lines on. We want to actually know for sure with numbers how well a line fits that data. So let's do that now. We're going to have a guess for the line of best fit. And we're going to compare our guess with the machine learning method later on, and you'll see how good the machine learning method is. So, wguess, bit of terminology here. Instead of using the gradient, I'm going to use what's called the weight. Let me explain this in a second. I've chosen these values, and B guess is 10,000. Okay, W and B. You're probably thinking, what are they? Well, normally when we do a line, the way I learned in high school was y equals mx plus c, where m is your gradient of your line, and then c is like your y-intercept. So in machine learning, different terminology, because we often use multiple dimensions, which you can't really just call it c in the gradient. It's just different terminology. So in machine learning, y equals w x plus b, and w stands for weights. If you've looked into neural networks before, you might have heard the terminology weights. Well, it's the same thing. The weights they're like your all those lines in those fancy diagrams. I'll put one on the screen for you. And then b is your bias. But for today, you can just think of them as a different way of saying gradient and y-intercept. So that's all w and b is. Okay. So, bit of terminology out of the way. Let's plot this line. So I just want to get a whole range of x values and then find the y values according to our line equation. The y equals wx plus b. So let's get a numpy array of our range we want the line to go from the 0th x value all the way to the 1400th value, so the line stretches across the screen. 14,000th value, sorry. That's it there. Excellent. Y line equals numpy array. This is where it gets a little fancy, and we're going to put our equation in. So yx plus b. So all we're going to do here is do w guess, right? W times x, which is our x line values, plus, you guessed it, b guess. Cool. Okay. All we're going to do is just plot that line now. So let's copy this here. Make that nice and easy. And we're going to do a plot. So bear with me as I change this. Plot, and we're going to do x line, y line, the color, let's go green, and we don't need marker for the line. You could do width, but it's a good width already. So let's check it out. Okay, so our guessed line is this green line here, and it looks pretty good. I mean, it fits visually, it seems to fit the data pretty well. So, but we actually don't know how dense the data is, just because it's just a purple cloud. There could be lots of data points right here, but we can't see that. We don't know. So we actually don't know how well this line fits all the data. Because, for one sake, imagine all the data points were actually exactly this point here, and there are a few more scattered around here. On average, this line would not fit the data well if there were like 1 million points right here, but we couldn't see it because they overlapped each other. So we want to have a way of actually quantitatively working out how well the line actually fits the data. So if the line fit perfectly, every data point would fit on the line, right? And if we had new house data that came in, we would expect that that data would fit on the line as well. That would mean that the line fits the data and is also a good predictor of future data, right? So that's our goal, but we need to quantify that. So a simple way of doing that is you go, okay, well, there's the line, and here's a point down here. Well, the distance from the point vertically to the line, well, that can be a measure of how off the point our line is from the actual data point. And if we do that for every single data point in the whole graph, then we'll get like a total error. So that's what we're going to do. We're going to have an error calculation. So let's start with 1 point, and then we'll work with all the points to give us a good picture. So for 1 point, let's work out the error of the 1500th point. It's just a random value. So error, well, I've chosen this beforehand, but you can pick any point you want. So the error I'm going to define by is, we want to look at So let's just say it's this point here. Our error is going to be defined by so for an x value, let's say, so this point here, its x value is somewhere around 13,500, something like that. So let's say for 13,500, for a data point at 13,500, what is its actual y value, right? So about $2 million. And then if we put it into our special equation up here, what is the predicted value, which will be the green line vertically above it? What's the difference between the predicted value and the actual value that we get in terms of price? So this is our actual value, right, for the 1500th point. And we want to work out the difference between that and the predicted value of the 1500th point. So 1500th point. Right, so that's the error. I'll print this error. So the error is $491,000. So we don't actually know where this point is yet. It's somewhere around here, I think. But let's plot it just so you can see it. So visualize the data. Okay. I'm going to plot a vertical line in yellow. And this vertical line is going to go from the 1500th data point. So the 1500th data point is going to be an x value of x dot values 1500th, right? And a y value of y dot values 1500th. So that's plotting our first point, so x and y value. That's plotting our first point. And then our second point, which is the second part of each of these brackets, is going to be, again, the same x value, but this time it's going to be the y point is our predicted y value, our predicted price for that x point. So this is where we put our equation in. This one here. Excellent. So we don't actually want the x line, we want the x values, 1500th x value. In fact, you know what? That there should be there. Okay, alright. We're in business. So that's a bit better. Okay, that makes more sense. So it was actually made a mistake back there. It was actually 591,000. Okay, so let's have a look here. So I've plotted it out. It should make sense now. Our 1500th point is where this yellow line stops down here. That's our purple point here that we're looking at. And the distance of this point, using the y-axis, our price, the difference in price between it and the predicted price for the same x value is the length of this yellow line here. So that's our error. And that error was $591,000. So $591,000. So now we have the error for one point. Let's work out the error for every single point. Okay, so to do this, you might just think, all right, let's just calculate the error for every single point and add them all up. So let's just give this a go. First of all, I'm just going to copy some of this in just so we've got it all in one section, just so it's easy to see. So, and we want to visualize the data. And then we want to work out the error. So the error. So we've got the error here. So remember, this stuff here, I've just copied it from before. It should be in the system, but I just like to see everything in front of me. So we've worked out, we're plotting our line, our green line, and then we're working out the error of one point to that line. But let's do it for every point. So for I in range 0 to, we need the total amount of data points. So to do that, rows, columns, just data frame 2D dot shape. All we're doing here this data frame 2D, that's our, our data frame with just the price and square foot living columns, or features we should call them. The dot shape method essentially just returns, or the dot shape, that just returns how many rows in the data and how many columns. So we're going to have 2 columns, and the rows is what we're interested in because that gives us how many data points we've got. So for I in range to, for every single data point, that's the rows here. So for every single data point, let's work out the error. So we don't want the 1500th error, we want every single error. Right, so remember the error is just the terminology we use for the distance between each point and the prediction line. So, error. Cool. Now, if we want to add all those errors together, we need to sum them together. So, error sum equals, we'll do a cumulative error sum, and because we're good coders, we'll initialize it. Excellent. Error sum plus our error. So we're going to just keep adding our error to this sum, and then we'll print the sum. So let's see what this does. And if you've done this before, you're probably thinking, well, that's not going to work. I'll show you why. So our error sum, let's have a look here. Oh, missed that. Okay, so our error sum, it's not that big actually, and it's negative. So you can see there's a problem here, is that most of the data points are below the green line. So they're all going to be negative errors. But the data points above the green line, well, they're going to be positive errors. And when you sum them together, they'll cancel each other out to a degree. So we want to add all the error together. So we need a way to find the absolute value of every error. And simple way of doing this is just to square it. So that's what we'll do. So we'll have error squared. Let's try that now. Excellent. That's more like it. So there's the value. Our points, there's lots of points, lots of errors, and they're all adding up to this big value here. So last thing we're going to do, this is just a bit of machine learning best practice, is we'll just use what is the standard total error calculation. And we call this, when you add all the errors together, we call it the cost, the total cost, right? So our cost function, which is how we calculate the cost, terminology is, we call it J. J is going to be our error sum multiplied by 1 over the number of rows. And for some reason, we actually do 1 over 2 times the number of rows. I know it's just another scalar, but that's just the way we do it in machine learning. I'm sure if you read up about it enough, it'll explain it somewhere. But let's just put brackets around here. That's your cost function. 1 over 2 times the number of data points times the sum of all the errors. So sum of all the errors squared, which we did back here. Okay, let's print our total cost. Okay, so the cost of the line is string J. Excellent. So you can see the cost is actually less because we've divided it by the total number of, sort of averaged it, I guess. So get rid of that one there. That's our cost. So we have a quantitative way of describing how well that line fits the data. And the perfect line would have a cost of 0, right? That means all the lines, all the points would have 0 distance between them and the line because they'd fit on the line, right? So let's just mess around with this line a little bit before we go to the machine learning so we can see how the cost varies when we get the line better or worse. So we want to record this. Tell theta to record when you mess around with an algorithm, to record what variables you changed, just in case you write, I don't know, a paper on it or something like that later. You want to know what you actually did to change it. So we had W equals 500 and B equal to minus 10,000, and our cost was this. Cool. Now let's try W is 1,000. So the gradient is going to go like that, and we'll do the same, the same y-intercept, the same bias. You can change the bias if you want. It'll just move the line rather than change the gradient, but up to you. I'm going to do it this way. Let's change that and see what happens. Okay, so there's a line. It doesn't fit the data very well at all. So you can see the yellow line, it's longer distance for that point, and you imagine that for all the points. And that's right, you guessed it, our cost is greater. Look at that, it's almost 10 times greater. See the decimal point there gives us the info there. It's almost 10 times greater the cost. So that means that line does not fit as well as this line. Let's try one more, and then we'll get to the machine learning. Let's try W equals 100, and we'll keep B the same, minus 10,000. Okay. That. Oh, okay. And that doesn't look like it fits as well, but let's have a look. So if you compare, so the decimal's the same spot here. So we look at the front here, 17, and there's 10. So this line here, actually fits better than the line that went through the middle like that. What does that tell us about our data? That means that there's actually a high density of data down the bottom here. Otherwise this line wouldn't fit as well as the one going through the middle. So we've got a bit of a picture of our data now. But importantly, we have a quantitative way of describing how well a line fits the data. Cool. Okay. Now we can try our machine learning algorithm, and we can actually know if it fits a line that's better or not, because we can quantitatively describe that. So let's get to the cool part, what we're all here for, which is the machine learning. So we're going to use a machine learning method called ordinary least squares. Check it out on Wikipedia. That's what I did, and there's a bit of math to it, but it's really quite simple actually. So the maths, so I'll type it out so you know what it is. Ordinary least squares method. And if you go to Wikipedia, just check it out. For 2 dimensions, the math's quite simple. For more than 2 dimensions, it's really quite cool, and we'll look at that in the next video. But the equation goes like this. To calculate the perfect gradient to fit this line, right? To calculate the perfect gradient, and then you can actually derive the y-intercept or the bias from that as well. But to find the perfect gradient or the perfect weight, our weight is going to be equal to the covariance of x and y divided by the variance of x. Simple as. We've got NumPy in Python, which does this stuff for us. So this is going to be really easy. So let's get to it. So first of all, I'm just going to convert our x and y data to NumPy arrays, so we can do cool things in NumPy with it. Bit of linear algebra. So x values, right, and then y values. We call that capital Y. Cool. Okay. What we're going to do is implement this equation. So our weight is going to be numpy.covariance between x and y, and it's going to be divided by the numpy.variance of x. Now, before we get into this, let me just explain how covariance works in NumPy. Covariance actually gives you an output like this. Don't ask me why, but it's just the way it is. it gives you the covariance of x by x, and then x by y, and then y by x, and then y by y. So we want this one here, which is what we're asking for anyway. So we need to actually index that. So simply all you got to do is just go the 0th list, this one here, and the first element, this one here. Cool. Okay, so that'll work. And the variance, it just works as it should. So we've got W. Now the bias we calculate, it's a bit like y equals mx plus c, but instead of using, or wx plus b, we're actually going to rearrange the equation, and we're going to put in the mean values for x and y. So check it out on Wikipedia. Mean y minus w times numpy mean of x. So that's simple. That gives us the perfect, you're just going to have to trust the maths here, or look it up on Wikipedia why it works. It's pretty cool. That gives us the perfect weight and the perfect bias to find the line of best fit for our data. Really cool. So now you can actually do this on paper. I wouldn't use thousands of data points to calculate on paper. It'll take you lots and lots of time. If you have a quick look at this, see I've done this little graph. You may not be able to see this. I just did like 6 points and then did the covariance and variance and calculated the y-intercept and the gradient, and look at that. So you can actually BXL on paper, which is kind of cool. So yay, ordinary least squares method. Anyway, let's plot this and let's see how it looks. So what I want to do is we'll just copy just about, we'll copy the lot. Actually, we don't need all of it. We'll copy this. We want to work out the cost of it, remember? It gives us a quantitative value to actually judge how good this line is. So we're going to use W and B, right? The cost of the line of best fit is, and the last thing we want to do is visualize the data. So we'll copy this again. We want to visualize this data. We'll also grab this so we can compare. Right. Now we need to actually plot this line. So I'm actually going to grab this bit from here, use that to plot our new line, which is the line of best fit, which is just W and just B. And we'll rename these variables best fit, line of best fit, and last thing to do is just plot the line of best fit. Let's do it in blue. Line of best fit, line of best fit. Sweet. Okay, so check that out. Blue is our line of best fit according to the machine learning ordinary least squares method, and green was what we thought was pretty good. Now, can we believe that? Well, let's see. The cost of the line of best fit, which was here, now the W and B value, I'll actually show you what they are, but the cost is this. And if you look closely, see the decimal where it is? So it's higher, there's less numbers in front of the decimal. So we've got a cost that is about 3 times smaller than the cost of our line of what we thought was best fit. So we've got the line of best fit using machine learning. Pretty cool. Now, let me just show you what the W and B values are, because that's kind of cool to know what they are. Print W, print B, right? So they're our W and B values. So let's see how close we were. So W is about 280. We'll just approximate for these. And the B value is 43,890. rounded there. So see, we were actually pretty close. But it's found the optimal value. Optimal value is to plot that line of best fit. So that's machine learning working in 2 dimensions. The full code. What we did is we imported the libraries, we read the CSV data in, we took in just 2 columns of the CSV data, which was the price and the square foot living area. We then applied the ordinary least squares method using the covariance of x and y divided by the variance of x. We calculated that and the associated bias value or y-intercept. We then worked out the cost and then plotted our line of best fit that we calculated, and we can evaluate how good that is by comparing the cost to other lines in the data. So that's it for today. Join me in the next video where we will go through multi-linear regression, which will be using more than one input feature to work out the price.